Hello and welcome back. In this video, we're going to be covering generics, which help make our code more reusable when using different data types. Hey, Future Colton here. The first half of this video heavily focuses on creating integer linked lists. Now, if you don't care or are unfamiliar with linked lists or other data structure implementation, you can go ahead and skip to this timestamp right here, and it'll just give you a very general high-level overview of generics and how they make our code more reusable and flexible across applications. In the future, I will make sure to cover other data structures and their actual implementations, so that would include linked lists, trees, and stacks, and maybe a few other data structures. Let's get on with the video. To demonstrate generics, we're going to give a fake situation. The government has suddenly stopped us from using arrays and slices and various other data structures in our Go programs. Now you internally freak out because how else are you going to store a series of data? So your first solution might be to come up with your own linked list. So let's start down that path. I'll make a linked list. So type int linked list because we want to store integers, which is going to be a struct. And then within this, we're going to have another type, which is of type node, which will also be a struct. And you don't need to be familiar with how linked lists work or anything, but this is just going to be a quick example. So every node is going to have a value that is of type int, and then it's going to have a pointer to the next value. So we'll have next be a pointer to another node. And our encompassing data structure here, the linked list, will have a head that's of a node type, and then we can also just have a size, which is a uint. And there we've quickly generated a linked list that only holds ints. We can go ahead and create an add method for our linked list, so therefore it would just be func, and we can use the method receivers that we've learned in a previous video. So I will give it LL to stand for linked list, and it will point to an int linked list, and it will be called add, and we're adding a value that is of type int. Now, when it comes to adding into a linked list, new node is equal to a node with the value set to the val that we were given, and then the next pointer set to nil. Now to insert into this linked list, we first have to check if the head is nil. If it is nil, then that means we have an empty list, and therefore our new node will be the only node in the list. So if linked list head is equal to nil, then the head will be equal to the new node. Otherwise, the head is not nil. So then we just say the new node that we've created, its next value is going to point to the head of the list, and then we'll update the head of the list to point to new node, so that we still preserve the original value. And then at the end of this, we just need to update the size. So we'll say ll.size++. And lastly, we'll do a quick toString function. So func on a linked list that is an int linked list, and we'll just call it toString, even though this isn't very idiomatic. Open up the braces, and we'll have a node called temp. So temp is going to be set equal to the linked list head. And so while temp is not going to be nil, we will go ahead and do a format.print line of temp.value, and then we'll update temp to be equal to its next value. So let's go back up to our main function, and let's create a new linked list. So ll is equal to a new linked list, so int linked list. Then we'll call add once with 1, then ll add 2, and then lastly we'll do ll.toString, which I'm actually printing a toString, should only print a string, but it's not a big deal. So let's go ahead and run this. So go run period, and we get 2 and then 1 printed because we were pre-pending each node in the list rather than appending. So we have the basic functionality of our linked list here, but we have an issue. Let's say that we have a teammate and they say, okay, I really liked your linked list, but I need a string version now. Or maybe another team member needs a float 32, or another person wants a cat linked list. And you start quickly worrying, and you're like, I have to basically type out all of this boilerplate code over and over again. How can I possibly get this done? And so then you start getting duplicate code everywhere. Every time you want to add or tweak a method, when you find a bug, you have to tweak it in 20 different spots, and it quickly becomes a headache. Now, during Go's inception, it originally didn't have generic support, and that was one of the biggest drawbacks at the time. But with enough brain power and effort, Go finally released generic support, and now we can demonstrate it in this video. Our first step in creating a generic struct will be to first add any at the end of our type name. Now, conventionally, we use single capital letters to represent a type that will be generic, so I will use T, and then you're supposed to give what kind of necessarily, I guess, type that you are willing to accept. And so I will put any, which means we will accept any type for a linked list. Additionally, we can go ahead and remove this int linked list so that we're no longer referencing that we only hold ints in this linked list, and we must subsequently update our node struct. So our node, which actually holds any values, will go right after the node name. And so when we need to update a field in the node, we just add t to the end of it because it's going to hold the same type as what the struct accepts. Now, as for our value, we also need to fix that because this is still only holding t, but instead of holding ints, we just add t to the end and also update our node up here to hold of type t. And there we go. Our struct declarations are done and ready to support any type that we put in it. And now the support for a generic linked list becomes much easier. For our first function that we implemented, what we need to do is change that name back to linked list, say that it's holding a type t. We are no longer only accepting ints, so the value is going to be of type t. And then we also have to declare right here that it's going to hold type t. Nothing else in our logic needs to change. It's that simple. For our toString, it will be something similar. We add the t at the end, remove the int from the very front of our name, and that's it. So now let's go back up to our main function, remove the int part from the very first piece. And now when we want to use a struct that is going to hold a particular data type, we just add the braces at the end, say what type we're going to hold, and it's that simple to create a generic struct. So when I go back down to the terminal, I do a go run period, we get 2 and 1 printed out to the console again. Now you might be thinking, okay, this linked list can hold any type, but remember, it can only hold the type that you declared when you initialized that struct. So when I go down here, I cannot do an ll add and then give it some string. The compiler will go ahead and catch that error for us. And just to demonstrate, let's make another linked list. So ll2 is going to be a linked list that's going to hold type strings in it. And I'll do ll2.add. We'll do colon, save it. Let's do another ll2.toString, save, go back here, run it. And there we go. We get our first integer linked list printed out to the screen, and then our string linked list printed next. And that's it for the video. I just wanted to give a quick high-level overview of generics in Go and how to implement them. If you made it this far in the video, I encourage that you like and subscribe, and I'll see you in the next one.